All right, this is the first of probably several lessons that we're calling comprehensive review. These are skills that are going to eventually be needed in geometry, but big picture, these are also skills that you're going to use in future math classes, possibly even those high stakes tests that are coming up. So sprinkled throughout the course, we'll kind of pause on the regular geometry curriculum and take a step back and make sure we strengthen some skills that will eventually be needed in future lessons. So this particular lesson, as you can see, is on simplifying radical expressions. And in particular, our focus is going to be on square roots. Now, eventually, we'll probably expand this into cube roots and fourth roots, but the process that we're going to cover is really going to be the same methodology that's going to be used when we do these other roots, but obviously it'll be a little different because we're looking at numbers that have perfect cube roots, numbers that have perfect fourth roots. Today we're going to primarily focus on numbers that have perfect square roots. And if they don't, then how can we simplify them with numbers that do have perfect square roots? All right, so let's just take our first example here. So this first example is nice because 25 does have a perfect square root. And so just to make sure we all understand what this radical means, we're talking about some number, I'll just call it x. When multiplied times itself, since it's a square root, then some number times itself will equal 25. Now you might be thinking, and I hope you are, that, well, isn't that true of negative 5 also? And yeah, it is, but anytime you see a radical like this, even though technically there are two different numbers that fulfill this, whenever you see a radical, it's always asking for what we call the principal root. And that's not something I'm going to ask you on a test, but some of you are inquisitive, which is really, really good. And I just want you to know that, yeah, there are two possibilities, but when it's being in radical form and we're asked to provide just the principal root is the positive. When there are two choices, the principal root will be the positive of those two choices. Okay, so that takes care of number one. Now let's take a look at number two. A little different story, because if we think about the numbers that do have perfect square roots, and I'm just going to make a quick little list over here. These are what we would call the perfect square numbers, and we don't have to go forever. Maybe we'll just go one more to cover number 4. Well, 45 isn't in this list. So the next best thing to simplifying radicals that do not have perfect square roots is to find one of the numbers that we would consider to be perfect square numbers. And if there's more than one, that divides into this, we call this the radicand, the number that sits underneath the radical. We want to find the number that divides into this number evenly. It's got to come from this list. In some cases, there's more than one. And if there is more than one, we're going to choose the biggest one off of this list. Well, there's only one of these numbers that divides evenly into 45, and that's 9. So the way we're going to simplify these, I know there are other methods out there. There is a factoring, prime factoring method that is great, but I think you guys are ready to handle this method, which really utilizes our knowledge of these perfect square numbers in a factoring process. Okay, so my blue, it's very important that the blue has to multiply. Notice it's factoring. Factoring means another way of representing the square root of 45, but I'm using multiplication of 2 or more factors. Well, in this case, it's just 2. So the key is picking a perfect square number as one of your factors if it exists, and then the other number will not be a perfect square number. Okay, so the simplification of this will be the square root of 9, which is 3, all right, non-radical, times the radical square root of 5. So if you think about it, the goal is to get as much of this number 45 out from underneath the radical as we can. And we got a pretty big chunk. If you notice, we started off with the square root of 45, and our answer just has the square root of 5. Okay, so that's kind of like the aim, the goal is to see how much of this we can get into non-radical form. Okay, so for number 27, same thing. It happens to be the same perfect square root number that divides into 27. That's 9. But this time I'm going to have to use the square root of 3. Those two equal the factoring. They equal the square root of 27. And I simplify the perfect square, and then the other square root of 3, of course, will stay radical. I can't simplify that. So that would be my answer for number 3. Number 4, same idea. I first check to see if the number itself is in the list, and 80 doesn't have a perfect square root, of course. So now my goal is to pick the biggest number. Now in this case, I've got choices. 4 divides into 80, but 16 also divides into 80. So when I've got choices, I want to always go with the biggest. Otherwise, I'll have to go through this simplification process again. And let's not go through it twice when we could just go through it once. So the square root of 80 is the square root of 16 times the square root of 5. 16 times 5 is 80. And now the square root of 16 becomes 4. And I can't simplify the square root of 5, so it stays radical. All right, so there's some examples of just numbers underneath square roots and how we simplify them when they do have a perfect square root and when they don't. Okay, now we're going to throw variables into the mix. Well, let's first do the number like we did before. All right, so the square root of 20. Well, 20 isn't a perfect square root number, but 4 is, and 4 divides into 20 evenly. So I'm going to represent the square root of 20 as the square root of 4 times the square root of 5. So my way of thinking about this is this left radical, the first one, will contain all perfect square numbers and variables. Everything in this first radical will be able to simplify, and nothing in this second radical will simplify. Okay, so the way we simplify variables is we do division. All right, so remember, for a square root like this, there's an invisible 2 in this area. It's called the index. And so if you want to know how to simplify variables that are in radicals, then just do this simple division. You're going to divide the index into the exponent. All right. Well, the problem here is it would literally be like this: x to the 3 divided by 2 power. Well, that's going to be a decimal, and we want just a regular whole number integer result. Okay, so 2 doesn't divide into 3 evenly, so the next best thing to simplify x to the 3rd is to change it into an exponent that 2 does divide into evenly. Now obviously I can't go above 3. Remember, factoring means I'm multiplying these two blue radicals together to make it equal the red. So it's got to be less than 3, and it's got to be a number that 2 does divide into. Well, there's only one choice. That's x to the 2nd. Now I've created x so that it is a perfect square variable because 2 divides into 2. And then to make it equal to x to the 3rd, I've got this leftover x to the 1st over here. And this is the bad radical. Nothing over here simplifies. These are all going to stay in radical jail. Okay, now y to the 5th. We got the same type of problem. 2 doesn't divide into 5 evenly. So we're going to turn this left radical, we're going to use y to the fourth because 2 divides into 4 evenly, which means I've got a leftover y that I'm going to put over here. All right, now z to the sixth is good because 2 divides into 6 evenly. So z to the sixth would be considered a perfect square root variable. Anytime the root divides evenly into the exponent, it's already perfect. No need to break it up. Okay, so this left radical will be completely simplified, non-radical. The square root of 4 is 2. This is another way of saying x to the 2 divided by 2 power. Remember, it's exponent divided by root. 2 divided by 2 is 1. Y will be to the, to show you over here, the 4 divided by 2 power, which is y to the second. And z will be to the 6 divided by 2 power. Everything, all these exponents get divided by the root, and that would be z to the third. Now this right side radical, these are all leftovers. They can't be simplified. They stay radical. And so this ends up being my answer for number 5. All right, let's take a look at number 6. Same problem. 18 doesn't have a perfect square root. So I'm going to use the square root of 9, which does, and I'm going to multiply that times the square root of 2, which does not. Okay, so perfects, not perfects. Good guys, bad guys. Okay, so a to the fifth. Well, again, 2 does not divide into 5 evenly. That means I'm going to turn this into a to the fourth, making it perfect. 2 does divide into 4. And so to make it equal a to the fifth, I'll have to put a over here on the right. B to the fourth is good already because its exponent, 4, is divisible evenly by 2. So we're good there. But we'll have to do a little work on c to the seventh. 2 doesn't divide into 7 evenly, so let's make it c to the sixth, which is perfect, divisible by 2, and then c to the first over here. And you should always check, make sure these two multiply together to equal this original. 2 blues multiplied together should equal the red. And now this left radical becomes the square root of 9, which is 3, a to the 4 divided by 2 power, that's a to the second, b to the 4 divided by 2 power, and c to the 6 divided by 2 power. And then this other radical, if you do it correctly, will never simplify. There will not be anything under here. So if you're doing this and you notice, hey, something under there can be simplified, then you know you have not gone through this process correctly. And you'll need to keep going until it is fully simplified. All right, let's take a look at number 14. 56 does not have a perfect square root. So let's use a number that does have a perfect square root if it exists. If there was no number that divided into 56 evenly, that's a perfect square root number, I would have to put it all over here. But as it turns out, 4 divides into 56, and it goes 14 times. A to the second, well, 2 is divisible by 2, so for the time being, I'm just going to show that a to the second goes with the perfects. It's a perfect square root. B to the fourth is 2 because its exponent, 4, is divisible by 2 evenly. However, c to the fifth is not perfect. So we're going to break it up into c to the fourth, which is, and then the leftover c is going to go over here in the leftover group. Now simplify the left radical. The square root of 4 is 2. The square root of a to the second, that's another way of saying a to the 2 divided by 2 power. That's a to the first. B to the 4 divided by 2 power, b to the second. C to the 4 divided by 2 power, c to the second. And then square root of 14c, which cannot be simplified. All right, very good. Now let's take a look at quotient property when we have a radical of a fraction. So we could say this: the square root of a fraction is the same thing as the fraction of the square roots. All right, I just kind of rephrase the quotient property a little bit. It really just means when you have the square root of an entire fraction, it's the same thing as if you had the square root of each of these numbers separately. And vice versa. If you started off with the blue, if you needed to, you could rewrite it as the red. So just do the square root of each. The square root of 25 is 5. The square root of 16 is 4. That one's nice because each of the numbers had a perfect square root. We're all good. And the same thing for number 9. Showing the quotient property, it's one radical of a fraction. So that could be the fraction of the two separate radicals. That's really just what the quotient property says. The square root of 49 is 7, and the square root of 36 is 6. Now, there are times when, like number 10, we have a fraction and we have a radical in the denominator, and that denominator cannot be simplified. Okay, so just for the time being, I'm going to come back to this problem, but let's just pretend like I had this. Well, if I had this situation, that's pretty easy because really that's just 2/5. But the problem here is there is no perfect square root of 3, and there's another problem. It's just a rule of math in general, the math classes that you're going to be exposed to, well, now, from now till May when you're done with geometry, and then going forward, you're not going to be allowed to leave answers that have a square, any root, a radical in the denominator. So the way we take care of getting rid of the radical in the denominator, it's a process called rationalizing the denominator. And here's how we do it. Pretty easy. The radical in the denominator is the square root of 3. So I'm going to multiply by that on the top and the bottom of this red fraction. And let's see what happens. So the goal, if you remember, is just to get rid of the radical in the denominator. And by multiplying by that radical, let's just go ahead and jump to the denominator. You're going to end up with the square root of 9, which is 3. So I started off with a radical in the denominator, and by multiplying by that radical, I have turned it into just a regular number in the denominator. And that's what rationalizing is all about. So now let's go ahead and finish off the numerator. So this just is 2 times the square root of 3. And then, of course, it's over 3. So we have, to use the phrase, we have rationalized this denominator. All right, let's try another one. So on number 11, you're not wrong if, in this case, you went ahead and did the square root of 18 multiplied on the top and the bottom of this fraction. That would be perfectly okay. The problem, I think, is you're going to end up doing 18 times 13, which is kind of a big number to try to find the square root of, even though you do have a calculator. So what I'm going to do is I'm going to go ahead and simplify the square root of 18 first, and then make the radical a little smaller, a little bit easier to work with. So I'm going to leave, for the time being, I'm just going to leave the square root of 13y. And I'm going to rewrite, remember what we talked about earlier in the beginning of this lesson. The square root of 18 could be written as the factors square root of 9 times the square root of 2. And this simplifies into 3, and then of course this does not. So 3 root 2 is just the simplified form of the square root of 18. Okay, now I'm just rationalizing the radical in the denominator. Okay, rationalizing. So I don't have to multiply by 3 root 2. I just need to multiply by the radical. I just need to get rid of the radical in the denominator. That's what this process is all about. Okay, essentially I'm just multiplying by 1. Okay, so multiplying these two numerators together, I got the square root of 26y. Now, in the denominator, I've got a regular number So I'm just going to set it aside for just a second, and now I'm going to multiply these two radicals together. So these are everything is being multiplied together. The square root of 2 times the square root of 2 is the square root of 4, which is 2. Okay, so the result of multiplying these two radicals is 2. Well, now I have to multiply 3. Now I can multiply 3, now that 2 has become a regular non-radical number, I can multiply them together. And so that ends up turning my denominator into 6. 3 times 2. Okay, now we want to see, maybe sometimes we go through this process and the numerator can be simplified. So let's take a look at 26. 26 is not a perfect square number. There is not a perfect square number that divides evenly into 26. And you might think 4, but 4 doesn't go into 26, it goes into 24. 8 is not a perfect square number. There are no perfect square numbers that divide evenly into 26. So this ends up being our final simplified, radical, rationalized denominator answer. Okay, we'll do number 12 in the same way. I'm going to just bring the numerator over for just a second and focus on the denominator. So the square root of 20, 20 doesn't have a perfect square root, so I'm going to use the number 4, which does, root 4 times root 5 to represent 20, square root of 20, because now I can simplify this as 2 times the square root of 5. All right, now to rationalize the denominator, I'm going to multiply by that radical on the top and the bottom. Just the radical. Okay, two radicals multiplied together. You just multiply these, all the radicands. 5 times 17 is 85x. So on the bottom, root 5 times root 5 is just 5. It's root 25, but root 25 is equal to 5. So just think about this, 2, now we can multiply times 5 since it has become, it went from radical to non-radical, and 2 times 5 is 10. So let's see, can we simplify the square root of 85? Well, 85 doesn't have a perfect square root, and we don't have any perfect square root numbers that divide evenly into 85, and so this ends up being our final answer. Okay, we're almost done. We still have to rationalize denominators, but sometimes the radicals are involved in either addition or subtraction. Addition here, subtraction, involving a whole number, a non-radical number, right? I should say an integer, because -2 is not whole, it's an integer. So in these cases, we're going to use something called the conjugate. And just very simply, here's how you can tell what the conjugate of the denominator is. So 5 minus the square root of 2, to get the conjugate, I multiply by 5 plus the square root of 2. The conjugate is just looking at whatever sign is in between. It started off in the red, it was minus. So to get the conjugate, I use the plus. You just do the opposite sign of what's between the integer and the radical. And we're going to multiply by that on and the bottom. Okay, so on the top, we're going to do the distributive property. 3 times both of these. 3 times 5 is 15. 3 times the square root of 2. On the bottom, whenever we have, we would, in algebra, we refer to these as two different terms. Those are called binomials. We use a process called FOIL. Maybe you've seen FOIL in the past. So FOIL stands for first, outside, inside, and last, meaning we're going to do multiplication. FOIL is really just another method of doing the distributive property. Okay, so F means let's multiply these first two, the red 5 and the blue 5. Those are the first of each of these expressions. So 5 times 5 is 25. O means to multiply the outside. So this red 5 is on the outside, and so is this radical blue, radical 2. Those are the ones on the ends, the outside. And 5 times the square root of 2 is 5 times the square root of 2, 5 root 2. Okay, so we've done F first, we've done O outside, and now let's do the inside. The inside would be this negative red root 2 times this blue 5. And when we multiply those together, that's just minus 5 root 2. So we've done FOI, and now let's do L. L means to multiply the last terms together. So it's going to be negative, because a negative times a positive is a negative, and then root 2 times root 2 is root 4, but that simplifies into 2. All right, so let's put it all together. Do you notice these two radical expressions, they cancel? Remember, the goal is to get a regular number in the denominator to get rid of radicals. Well, when the radical is involved with another integer like this, we have to use the conjugate, but the result is still going to be the same. We're going to end up with a non-radical denominator. So these cancel, and I'm left with 25 minus 2, which is 23. And so that ends up being my final answer. All right, let's go down to number 15. The conjugate of 6 minus the square root of 3 is 6 plus the square root of 3. Let's look at that sign in between and change it. Pretty simple. And so let's do the distributive property on the top. 8 times 6 is 48, plus 8 times the square root of 3. And now on the bottom, I'm going to walk you through FOIL again. So the F is red 6 times blue 6. That's the first two terms. That's 36. The O outside term, 6 times the square root of 3, and they're both positive. I, the inside, is negative, the red, negative root 3 times 6. And then the last will just be minus 3. Red radical 3, negative red radical 3 times blue radical 3. These will cancel. That's the purpose of doing conjugates. It makes our radical go away. And then I just combine 36 minus 3, and I got 33. Now, if we could, let me just mention this, if it were possible, now I'm not talking about the radical, but if it were possible to divide all of these three non-radical numbers by the same number, then we would do that. That's just called reducing. But you have to be able to divide all three of these by the same number. All right, so if it were 48 and 33 only, then I could do 3 into both of those, but I can't divide 3 into 8. So therefore, I can't reduce this. So this ends up being my answer. And the same thing happened up here. I mean, 3 goes into both 3 and 15. We're doing good there, but 3 doesn't go into 23. There is no number, now we don't count 1. There is no number that divides into all three of these non-radical numbers. You cannot divide into the radical. Okay, the radical is set. But there are occasions where you might be able to reduce these if it's possible to divide the same number into all three. Okay, so number 16 is our last one. The conjugate of negative 2 plus the square root of 13 is negative 2 minus the square root of 13. So pay attention to the fact that the first sign didn't change. What makes it a conjugate is we change this middle sign. All right, let's do the distributive property on the top. 3 times negative 2. Just separate this a little bit. 3 times negative 2 is negative 6. 3 times negative root 13. And then we'll do FOIL. So let's just walk through it. Negative 2 times negative 2 is 4. Negative 2 times negative root 13, that's plus. Negative times negative is positive. In the middle, though, it's going to be minus -2 times root 13. So again, your radicals should cancel each other out. And then 13 times root 13 times itself, this will be just regular 13. Okay, now -6 minus 3 root 13 all over -9. Okay, and I think we got to this point in class and we just ran out of time, and we need to, in this case, it is possible to reduce because you could say 3, but since they're all negative, let's say -3, we'll divide into each one of these. So it's got to be the biggest number that divides into each one of these non-radical numbers. So -3 goes into -6 twice. -3 goes into itself. And then -3 goes into -9. So it's not like I'm going to count this wrong on your homework today or next time we check if you forget, but I just want to give you a heads up going forward. There are times when we can take an answer and reduce it, only though if all three of these numbers are divisible by the same number. And in this case, we could divide -3. Oh, and I just realized -3 divided by -3 is not 3. All right, so this should be the answer. -6 divided by -3, -3 divided by itself. You could put 1 there, but it's not necessary. And then -9 divided by -3. So sorry about that little error. So that is your final answer. And so that is our lesson. We'll take a look at your homework the next time we meet. If you do have any questions, you're always welcome to email me, and I will see you next time.